Okay, now let's go to electromagnetic induction. Let's use the same symbol as for electromotive force. Electromagnetic induction is the process to induce current by the variation of the magnetic field strength in a circuit. Okay, we have different ways to do that. One way is changing the magnetic field strength. Another way is changing the area of a loop. Another way is rotating a loop inside of a magnetic field. Another way is switching on and off a circuit in another nearby loop. Okay, let's go to case one. In case one, we change the magnetic field strength. We can do it this way. At the beginning, we have this magnetic field. This is the loop by the circuit. When we increase the magnetic field, we induce a current, right? A current is induced. The same thing happens for case two, changing the area. Imagine that we have this area and we're moving this section. It's a conductor. We're moving this part, so we're increasing the area. If we're doing that, a current is induced through to this circuit, through the conductor. Also, imagine that we have a magnetic field, we have a loop. If we can change the area in this way, also we induced a current. Okay, another way is rotating a loop inside of a magnetic field. Imagine that this is the magnetic field right here, correct? And now we have a loop, that, now we rotate that loop. In that case, we also induce a current, or we have electromagnetic induction. Great. Another way is this one. Imagine that we have a section, an area where the magnetic field increases. If we take the loop moving inside of this change of magnetic field, also we induced current. Okay, let's go to one more time to case one. We have, for example, a magnet. Remember, the intensity of the magnet increases or changes, right? When we're going toward the poles. When we're going away from the poles, the intensity of the magnetic field decreases. Imagine this is the case, we have a loop, it's fixed, and now we move a magnet toward that loop. Well, the intensity or strength of the magnetic field changes, increases. In that case, we induce a current, correct? The same thing happens when we're moving away this magnet from the loop. But look, the current changes direction. In this case, goes, let's say, clockwise and counterclockwise, and in this case goes clockwise. So direction changes if we change, right? In this case, the direction of motion of the magnet. Now let's use the south pole. This is a north pole. Now let's use the south pole. The same thing, correct? If we're moving down, the current goes clockwise. If we're moving up, right? The current goes counterclockwise, changes direction. That depends again in the way in which the strength increases or decreases, correct? I'll explain this one later because this is all called the Lenz's law. Perfect. Again, these are the ways how we induce current in a circuit when we have a conductor inside of a magnetic field. These are the different ways. Perfect. Now let's go to the next topic, which is also let's try to find a formula that help us to explain this concept. Great. Now let's go to the next topic, and the next topic is gonna be the magnetic flux. Let's do it. Magnetic flux. The magnetic flux behaves in the same way as the electric flux. We already covered that section, that part. Electric flux. Now let's go to the magnetic flux. Okay, let's do it. Magnetic flux. Magnetic flux. Correct? The symbol is gonna be in this way. Right, flux stands for flow. Perfect. Imagine that we have a magnetic field going downward. Alright, imagine it's constant. For simplicity, this is the magnetic field. And we have a funnel right here, a funnel that is used to collect the magnetic field. Correct? Now, this magnetic flux, correct, depends on the area, right? The area of the funnel, correct? So this magnetic flux is proportional to a flow, right? Going through this section depends on the area. Perfect. Also, the magnetic flux depends on the angle, right? If we change the angle of the funnel, imagine it's a funnel one more time, and now let's change the angle, correct? In this way, well, in this case, we have not magnetic flux going through this area, or being collected, right? Means what? That the magnetic flux also depends on the angle of this collector, right? In this of this object, of this section, correct? Depends on the angle. If we remember in the previous previous chapters, we mentioned that area is a vector. We can take the area as a vector. If this is the area, now this is gonna be the direction. This is the magnitude, and this normal is the direction. Let's do the same thing right here. This is the area, right? And now this is the normal. This is the direction, right? This is the direction. When the direction of the area is parallel to the direction of the magnetic field, correct? We have the maximum magnetic flux through this area. Now what happens when these two are perpendicular? This is the magnetic field and this is the direction of the area, perpendicular. We have zero magnetic flux, right? Then in this case, we have a function that gives us that when the angle is zero, when these two are parallel, the angle is zero, we have the maximum, and when the angle is 90 degrees, we have zero or minimum, and that is cosine, right? Cosine 0 is 1 and cosine 90 is 0. So this magnetic flux is also proportional to cosine theta. Correct? Perfect. Also, if we increase the magnetic flux, also we increase the strength, right, of the magnetic field. Also we increase the magnetic flux, right? So we have these quantities or factors that are part of this magnetic flux. So what do we have at the end? Magnetic flux then is proportional to area magnetic field times cosine theta. How do we eliminate this symbol using a constant? The constant is used, remember, mainly to find the to match the unit, correct? But the constant is found to have a value of 1, and the units of the magnetic flux is the same as these units right here, correct? When that happens, the constant is just pure number 1. That happens in this case. So magnetic flux is equals to area V cosine theta. Okay, this is the magnetic flux defined as the area V cosine theta, cosine of the angle. Now, this is a new quantity. It has units. We found already the magnitude. Let's find the units for this quantity, magnetic flux. Okay, these are the units. If we are dealing with centimeters, right? For example, we get this one, and we can solve for B. Oh well, yeah. We can use. Oh, this is actually the units. Magnetic flux, right? Unit. Later we can go to the electric field. Magnetic field, correct? So these are the units. The units are called Maxwell's, right? Maxwell mx. This is in the CGS, right? Centimeters, grams, seconds system. Also, we have Weaver. Weaver is another unit. The Weaver is when we are in the MKS, meters, kilograms, second. Using this, actually one Maxwell, when we have a magnet, north-south, right? We have a magnet, correct? A magnet. This magnetic line is a Maxwell, right? This is one Maxwell, another Maxwell, correct? Now let's solve for the magnetic field. The magnetic field is equals to magnetic flux divided by the area. Let's take cosine theta equals to 1 for simplicity, and let's find out the units for the magnetic field. Okay, if we use Maxwell's, right, what do we have? Maxwell divided, the area is gonna be, because we are in centimeters, gonna be centimeters squared. These are called Gauss. Okay, if the unit for the magnetic flux is the Weaver, correct? So in this case we have that we are in the meters, correct, square. So this is Tesla. The symbol right here is G, right? G for Gauss, and Tesla, T. Correct. For example, it's found that one Weaver, correct, is equals to 1 Weaver is equals to 10 to the 8 Maxwells. 10 to the 8 Maxwells. Correct. Remember, if we have one square centimeter, there's gonna be how many, right? Square centimeter do we have in 1 square meter? Right? Of course, we have a lot. We take this area, or we take that huge area. We have more lines crossing, more magnetic lines crossing through that area. Okay, perfect. And also the relationship between Tesla and Gauss is 1 Tesla is equals to 10 to the 4 Gauss. To the 4 Gauss. Right, and these are the units for the magnetic field. Great. Now let's go to the case when we change the area of a circuit, and we call that the motional EMF. Go to the motional EMF. Okay, let's do it. Motional EMF. Motional EMF, right? Motional EMF. Perfect. Imagine that we have a conductor. We have a conductor right here, and as a reference, we use this lamp, right? As a resistor right here. And we have another conductor that it moves, right? It slides through this wire with it moves with some velocity. Imagine that this conductor is placed into a or inside a magnetic field. Imagine this is the magnetic field, correct? Goes inside magnetic field, correct? And at the beginning, this conductor was at this position, and later moves this distance delta x and keeps moving to the right. In this case, we're changing the area. We change the area. Of course, we induce a current right in that direction. Perfect. Now let's see what happens. What should be the a change in the electromagnetic in the magnetic flux, right? Because we mentioned that if this is the magnetic flux, one more time, magnetic flux is equals to my magnetic field area cosine theta. And from the beginning, we mentioned that how we can create or induce current in a circuit. Well, we mentioned that if we change the angle, when we rotate the loop, we induce electromagnetic force. Or when we change the area, could be this case, also we induce electromagnetic force. Or when we change the magnetic fields, we also induce electromagnetic force, right? Okay, let's do it one more time. Electromagnetic force, then, well, we have these cases for electromagnetic force that is proportional, right? Is proportional to the change in area respect to time, right? When we change the area respect to time, we induce an electromagnetic force, current too. Okay, also when we change the magnetic field, we have a change in the we just mentioned it before, right? Respect to time, we also induce an electromagnetic force. Also, when we change the angle, right? When we change the angle, or in this case cosine theta respect to time. But these three quantities are represented in the magnetic flux. So in general, we can say that the electromagnetic force is equals to the change of this magnetic flux respect to time, right? Because if we change the area, the magnetic field, of the angle, which are factors of the magnetic flux, we are inducing an electromagnetic force, right? Perfect. Now let's see what happens when we are changing, like in this case, the area, right? So let's go to this equation. We have that electromagnetic force then is equals to the change in what? Respect to time. The change of the magnetic flux. But the magnetic flux is B A cosine theta, right? In this picture, in this problem, in this case, the magnetic field is constant, the angle is constant, we're changing only the area. So we represent this in this way. We have B cosine theta times change in area respect to time. Correct? Perfect. Now, let's try to find this change area respect to time. This is the change in area right here, right? Change in area. But the change in area is, we call this the segment L, right? This distance L. What is there? It's going to be L times delta x. So delta A, the area, change in area, is equals to L times change in x. But let's try to involve this speed. How do we define speed? Speed is equals to delta x divided by delta t. Now from here, let's solve for delta x. Delta x is equals to v delta t. Let's substitute this value right here, and what do we have? We have that the change in area is equals to L v delta t. Right? Let's plug this value right here, and what do we have? This equals to v cosine theta. By the way, what is at the angle between? This is the angle between v and area. The angle between v and area is 0, right? These are parallel. So it's gonna be 0 cosine 0 is 1. We can just make this 1 right here, and let's substitute the value of change in area. It's gonna be L v, right, delta t divided by delta t. Perfect. So the electromagnetic force, we call this actually motional EMF, right, motional electromotive force, is equals to B, right, the magnetic field L times V. Right, and this is the motional electromotive force. Correct. Perfect. Now let's go to this part right here. We are dealing with this case. Correct. And in this case, we have this formula. It's a very important formula. It's gonna be electromotive force is equals to change in the magnetic flux with respect to time. This is when we have only one loop. What happens if we have n loops? If we have n loops, correct, we add these numbers of loops. But remember, when we have this magnet, correct, moving down with some velocity, we mentioned that if we have a loop, a conductor, a current is induced, and the current goes in this direction. Why it doesn't go in the other direction? Well, this is happening because when we have, remember, every time we have current in a wire, right, a magnetic field is produced, right? We have a magnetic field. Imagine that this current goes in this direction. If that current goes in that direction, the magnetic field goes in this direction, right? Using the right-hand rule, right? This is the right-hand rule. The same thing happens right here. When we have a changing magnetic field going downward because this magnet goes downward, and also we have a current right in this direction. Now we increase more the strength at this instant. If we increase the strength of the magnetic field going through the loop, we are increasing the current. We are increasing the current, we increase even the magnetic field produced by the current, and the current goes to increase a lot. The current goes to a big number. Even it can go to infinity, to infinite. It doesn't happen in nature. The current doesn't increase. The current takes some value, correct, at the end. Well, means that what is happening is that the current induced must be opposite in the way that the magnetic field opposes the change, the increasing of the strength of the incoming magnetic field. So it's gonna be opposite, correct? Otherwise, it's gonna be in the same direction. The current is gonna be increase. And that's happening in nature, in the experiment, right? What is happening is the opposite. The current goes in this way to oppose, right, the change of the external magnetic field. And to represent that, we use the sign negative right here. This sign negative is called the Lenz's law. Lenz's law. And the whole thing, this one, is called the Faraday's law. Faraday's law. Right? But this sign, negative sign, is called Lenz's law. And that is because, again, the current induced because of a changing external field must be opposite in the way that the magnetic field produced by the current induced must be opposite in direction to the increasing, changing external magnetic field, right? And that is gonna be represented by this sign, negative sign. And the whole thing is called the Faraday's law, right? The way how we can induce electromagnetic force, changing the magnetic flux, which are represented by area, magnetic fields, and cosine theta. Correct? Perfect. Let's start right here for this chapter. For this time, let's continue in the next video for the second half for this chapter. Okay, thank you. See you later.